Welcome to lecture 16 of the planets. And we had a special day today with a partial solar eclipse, a real treat, something that happens only once every few years. And just a few hours ago, the partial eclipse happened. With a show of hands, how many of you saw the partial eclipse? That's great. It was, I think all of you would agree, quite a moving, almost spiritual sort of experience to see the sun that shines every day of your life, this enormous spherical cloud of hot gas in which the nuclear reactions at the center power almost everything on the Earth. It glows every day, and yet a big chunk got taken out of the sun, at least as we viewed it, because the moon was crossing in front of the sun. So I'm going to tell you a little bit more about this partial eclipse that we enjoyed today. Here you see a little clip showing the point on the Earth over which the sun resided. I'll play it again. And you can see in the dark regions where the Earth was dark, due to nighttime, but there is where the Earth was dark because the shadow of the moon was cast on the Earth. It wasn't a perfectly dark shadow, as you can see, but you can see there in San Francisco we got some of that partial eclipse. I'll play it one more time. Right there. So for a couple of hours, the moon was orbiting the Earth and just happened to cross in front of the sun. This is very much the way it looked if you had glasses on that we had out there on the grass area. And if you use a telescope, I want to show you what it looked like here. And some of you got to look through the telescope that we had. Here's what it looks like. That's what it looked like 2 hours ago. And if you remember, there was an eclipse where the moon was crossing in front of the sun, blocking our view of the sun, and we were treated to a real unusual phenomenon, which is this sunspot group, which you could see with your naked eye. Just looking through the eclipse glasses, you could see the whole spot, and if you had good eyes, you could tell there was a spot here and a spot there. So it was really quite a treat to get both an eclipse of the sun and a beautiful sunspot cluster, a complex of sunspot activity. And in the second half of today's lecture, I'll tell you what causes sunspots and some amazing aspects of sunspots. What you couldn't see with your naked eye was that there were other spots here and here and here and here. This is an actual photograph of the sun, and these spots, these littler spots were there. You just needed a telescope to see them. And there are typically a few small spots, sunspots on the sun, but it's very rare to have such an enormous spot complex. Here's a little more graphically of what was happening in the last 3 hours. The moon crossed in front of the sun. Schematically, the moon actually crossed sort of over the top half of the sun, like that, from right to left. And the reason that happened is shown here in this schematic of a partial solar eclipse. You can explain this to your friends and parents and so on if they ask. Here's the Earth. We were located somewhere on the Earth, like where my laser pointer is, like say here. And the moon was in the way as it orbits the Earth counterclockwise. And the moon was partly blocking the sun. So if you're standing here, you could still see some of the sun, but you couldn't see other parts of the sun. So that's a partial solar eclipse because standing anywhere on the Earth, you could always see a portion of the sun, but the moon was blocking the rest of the sun. And if you hung out there for 20 or 30 minutes, you actually got to see the moon move across the sun. The actual bite out of the sun appeared to move from right to left, and that's simply because the moon was orbiting, that is to say, the moon was orbiting the Earth, slowly moving from right to left across the ecliptic plane, the orbital plane of the Earth around the sun and the moon around the Earth. Now, I'll remind you of something that I talked about before. You might be asking yourself, well, gee, isn't there going to be a solar eclipse every month? Every time the moon goes around the Earth, doesn't the moon get in the way of the sun? And as you know, the answer is no, not quite, because the moon's orbital plane is tipped 5 degrees to the Earth's orbital plane around the sun. So when the moon is in between the Earth and the sun, the moon in its orbit that's tilted might be a little above the Earth-Moon ecliptic plane, or sometimes the moon is below the Earth-Moon ecliptic plane, and only rarely do you catch it as the moon goes around like so. Do you catch it where the moon is like right in here, as shown in this diagram, where the moon is actually nearly aligned with the sun. So because of the tipped orbital plane, even when the moon is a full moon, well, that's when it's on the other side of the Earth. Even when the moon is a new moon, it's not necessarily right in front of the sun, because its plane might take it a little above the sun or a little below the sun. Now, last time we were talking about the interior of the sun, and let me just summarize everything in the lecture on Tuesday. We talked about the core of the sun, where it's so hot, 15 million degrees, that nuclear reactions can take place. Not just chemical reactions, which is the stuff of chemistry, but actual nuclear reactions. And we described in some detail how protons fuse with other protons, and that gives you deuterium. And deuterium fuses with another proton and gives you a helium isotope, and then that reacts with another helium isotope eventually to give you helium with 2 protons and 2 neutrons. Energy is given off. So the core is where all that energy production takes place by nuclear reactions, fusion of hydrogen into helium. You owe your existence to the energy produced every second of your lives in the center of the sun. And then that light gets out, the gamma rays, the photons get out by first winding their way in a drunkard's walk through the radiation zone, and then the hot gas at the bottom of the convection zone rises, convectively dragging its heat upward through the convection zone and heating the outer surface of the sun, and the outer surface of the sun is called the photosphere. It's essentially the atmosphere of the sun, and that's what your eyeball sees. When you look at the sun, you are, of course, only seeing the outer layer of gas, hot gas, 5,000 degrees, and then outside that layer is even hotter gas, the chromosphere, and then the corona. And we'll talk about some of that for the rest of today. By the way, there is a homework assignment due tomorrow about the sun. And just to remind you, it's all in chapter 14. Find yourself a quiet place for 3 hours. Read chapter 14 to learn everything that you need to know for the rest of your life about the sun. There's a homework assignment on the sun. So this was a golden week because we are studying the sun, and there was this partial solar eclipse that coincided with it. Okay, so let me now go back and tell you a little more about the sun, this time starting from the outside, the skin, the atmosphere of the sun. And again, when you look at the sun, let's say through eclipse glasses so that you don't hurt the retina of your eye. Remember, the sun is not only very bright and would burn a hole in your retina, but the ultraviolet light that comes from the sun would also damage the cells at the back of your eye. And so you can't look directly at the sun, as you all know, but through glasses, a dark, very dark filter, you can easily take a photograph of the sun. And this, again, is a photograph of the sun taken today. You see our friend, the sunspot group that we all saw with our naked eye if you were out there looking. So this is the sun taken just today, actually a few hours ago. But this is a picture taken in visible light. Remember, your human eye is only sensitive to light in a very narrow range of wavelengths or frequencies of light, between about 400 nanometers and 800 nanometers of wavelength. And you know that at shorter wavelengths, there's ultraviolet light, and longer wavelengths, there's infrared light, and so on. You can do some interesting things by taking a picture of the sun in different wavelengths that pick out different heights in the atmosphere of the sun. And one of the tricks astronomers play is to put a filter in front of the telescope that just allows light coming from hydrogen atoms. The sun is made mostly of hydrogen atoms. You remember I told you the sun is made mostly of hydrogen, 70%, and then another 23% helium. So if you take a picture of the sun just in the wavelengths of light that the hydrogen emits, this is what you see. And this is a picture taken today in hydrogen light. If you were lucky enough to be out on the lawn during the partial eclipse and you looked through that telescope we brought, this is what the sun looked like in part. It was red because you may remember hydrogen gas emits red light when electrons drop from the third energy level down to the second energy level. When that electron drops, it spits off a photon that has a wavelength that's red. And so you're seeing the red sun. There are patches that are not red at all. Some of them are very bright, like right here. And that should ring a bell. Right in here is where that sunspot was. And in fact, if we go back, there's the visible light image, and there's the image taken just in the light of hydrogen gas. And this kind of a picture allows you to see the temperature of the gas high up in the atmosphere, where the sun is still transparent, i.e. you can see it. And you can see that it's extremely hot. This white temperature and yellow-orange color tells you that it's hotter here than it is over here, as measured in this hydrogen light. And so something about that sunspot, which looks dark in visible light, looks extremely bright when you take a picture in hydrogen light. This must be telling us something. And what it's telling us, it turns out, is that the gas above the sunspot is extremely hot, hotter than the rest of the sun. In contrast, and I'll talk about this later, the visible light picture of the sun showing the sunspot, because the sunspot is dark, it must be cooler than the rest of the sun. Remember, the sun is emitting by thermal emission. It's hot, so it glows white hot. But a sunspot is dark, so it must be much cooler, and it is. And we'll talk about that in a few minutes. But in contrast, higher up in the sun, the gas, strangely, almost puzzlingly, is actually hotter than the rest. Something about what causes the sunspot is making it cool in the regular photosphere, but hot in the upper atmosphere. So this is an actual picture taken in hydrogen light. Let me now show you what the sun looks like today in X-rays. The sun is emitting X-rays. And here's a picture. taken today. You can see here is where that sunspot was, but now it's very, very bright in X-rays. In other words, there are prodigious amounts of X-rays, high-energy photons, high-frequency photons, coming from the sun right where we saw that sunspot. Something is happening there, and we're going to talk about it, that both makes the surface of the sun cool and therefore dark, but makes the upper atmosphere hot and bright in these high-energy photons. By the way, if you have a good memory, you might look at these other hot spots where the X-rays are coming out. If your memory is good, and of course I can help it, that's where there were spots, but smaller spots. Let's go back. You see there was a spot here, and here, and here, and here, and now we go to the X-ray picture. And you see spots here, and here, and here, and here, and here. And there's some where we didn't see a spot at all, but there's still X-rays. So whatever's causing the X-rays sometimes can happen even if there's no spot at all. Now, the clue, the essential clue to what's causing all of these phenomena, the enormous variety of cold, dark spots, hot, upper atmosphere, X-rays, and so on, the clue comes from measuring the magnetic field of the sun. You can measure the magnetic field of the sun with a technique that I could tell you about. It's called the Zeeman effect. But suffice it to say, there's an effect in atoms when a magnetic field is there that you can measure with a spectrum. And I want to show you now where the magnetic field is in the sun. Here it is. This is a magnetic field map taken today of the sun. There's today. And you can see this spot complex has a place where the magnetic field is depicted as black and white. This is the south pole and the north magnetic pole. South magnetic pole, north magnetic pole. South, north. South, north. These regions where we saw sunspots are associated with magnetic fields. And these turn out to be whopping strong magnetic fields, about 2,000 times stronger than the Earth's magnetic field that makes your compass needle orient toward the north. Here on the Earth, the magnetic field is useful. On the sun, it's 2,000 times stronger. And in these sunspot regions, the magnetic field is incredibly strong. The sunspots are obviously being caused by the magnetic field, as are the hot spots that we saw in the hydrogen light and in the X-rays. So all of these phenomena are due to the magnetic field, in the one case, cooling the gas to make it darker by thermal emission, and heating the gas higher up to produce ultraviolet light and X-rays. So the magnetic fields that come and go on the sun, and I'll talk about that in the second half of today's lecture, the magnetic fields are changing all the time, minute to minute, hour to hour, month to month, even decade to decade, and the magnetic field dynamism makes the sun an extraordinarily exciting place, a place where every day is different from every other day. Okay, so now I want to talk a little bit more about the structure of the sun and the surface of the sun. Let me remind you again, there's the core, there's the radiative zone where the photons carry the energy, then there's the convective zone, then there's the photosphere, the outer skin. There is this hot gas outside where the X-rays are produced in the corona. But I want to go back now to the properties of the photosphere and get myself to a place where I can explain the spots, the sunspots, and all of their interesting aspects. To start, let me show a clip that I showed last time. You can see the roiling, broiling surface of the sun, and that's because just beneath the surface, the energy is being carried by convection, hot gas rising. hot gas from below, carrying its heat upward, delivering the heat to the surface where we get to see it. And it's obvious just by looking at the movie that the hot gas is rising, delivering its energy, cooling off, and falling back down. The hot regions are these bright spots like here and here, here. And then the dark regions around the edge is where the cool gas, the now cool gas, falls down. Here, of course, you also see sunspots with a lot of structure. Let me first summarize what we know about the photosphere, the surface, and then we'll talk about the spots. The surface of the sun is bright, blindingly, literally blindingly bright, because it is so hot, 5,800 degrees Kelvin. It's a yellowy white color because it's glowing by thermal emission that you learned about before. The sun is hot, and that makes it glow by thermal emission. And as you recall, an object that's very, very hot emits most of its light not in the infrared, like your human body or the surface of the earth, but the sun is so hot that the thermal emission emits most of its light in visible light, not the infrared. And so that's why you can see the sun indeed blindingly bright, with the peak of the energy distribution from photons being in visible light, wavelengths of 500 nanometers or 600 nanometers. The sun is extremely active on the surface, and it's due to magnetic fields. It's not only hot, but magnetic. And the magnetic fields pierce the surface. They thread up and come down, carrying hot gas, entraining the hot gas along the magnetic field lines. So where the magnetic field pierces the surface of the sun, you get to see with your own eyes the magnetic field lines, because the gas is swept along, trapped in that magnetic field. So you see the convection, but you also get to see the magnetic field properties, the morphology. So to summarize, let's take a trip from the surface of the sun all the way to the center. Here's that trip. There's the photosphere. There's the convective zone. Inward of the convective zone is the radiative zone, where photons carry the gas. Photons carry the energy. And then in the core, nuclear reactions are taking place. Generating the energy that heats up the rest of the sun. Let's play that movie one more time. So here's the surface, the photosphere. And then beneath the photosphere is the convective zone, where energy is carried by convection. Then the radiative zone, where energy is carried by photons. And then finally the core of the sun, where the temperature is so high that nuclei slam into each other and engage in nuclear reactions to produce energy. So that's a synopsis of the sun. And it shows you all of the regions of the sun that we've been talking about, from the center outward or outward toward the center. Now, before I tell you about sunspots, I want to tell you that, today was exciting because we got to see a partial solar eclipse. But the luckiest thing that can ever happen in your life is to see a total solar eclipse. They are very rare. If you stand in one place on the planet Earth, if you live in one city on the planet Earth, your entire life, you'll probably never see a total eclipse of the sun. So I wanted to share with you some pictures people have taken during a solar eclipse that's total, a total solar eclipse. And there was one a couple years ago. Here in November of 2012, this path shows the shadow of the moon cast on the earth as the moon got in the way of the sun. And right along this path, the people who were on that path saw the sun completely blocked out by the moon, totally blocked out. And you could only see the corona on the outskirts. And I want to show you some pictures from that total eclipse. They're so rare. Here's the path right here, that red circle with a dot in the center. The dot in the center is where the path of totality exists. So let me show it again. Here's the path of totality. There it was total right over Australia, and then through New Zealand, and then over into the South Pacific. And of course, many people flew to Australia specifically to see the total eclipse. A great place is right here in the northern reaches of Australia. So if you lived in Australia in 2012, you could have driven up there if you didn't want to fly. And so many people drove or flew to Australia right in this path of totality, right in there, over the top of Australia. And so people stood right along this path in here where the eclipse would be total. Here's what it looked like approaching eclipse. People standing on the beach in Australia waiting for the sun to get blocked by the moon. People had their eclipse glasses. They had their telescopes out. They were all ready to go. It started getting darker and darker as the moon started covering the sun. And I'll show you some pictures of this. Here's a guy with his solar eclipse glasses, looking about as goofy as all of you did. And here it is getting close to totality. Here is now going back in time. Here's what that eclipse looked like at the very beginning. The moon is right here. And the moon is just beginning to cross in front of the sun. Here it is a few minutes later. They had clouds. They were worried. A few minutes later. And then a few minutes later after that. Takes about an hour for the moon to cross and cover the sun. And here's what it looked like when the moon completely covered the sun. When you take a long exposure, 5 seconds, 10 seconds with your camera, you see this wispy light outside the surface of the sun, and that's the corona. Very diffuse, thin gas, but extremely hot, 1,000,000 degrees. And if you take a longer exposure, you can see the corona around the sun more clearly. Again, this is the moon blocking the sun. Here's another picture of the corona. You can see some of the hot gas near the surface of the sun bubbling up, erupting off the surface, off of the photosphere. As the moon just leaves totality, there's a tiny glint of light from the surface of the sun that beams through. And here's a picture of that first instant when the eclipse is over. This is called the diamond ring effect. You can see why. Diamond ring effect. Beautiful, huh?
Does that also happen when it's coming to cover?
It does, yeah. Thank you for asking. This diamond ring effect happens both when you're just before totality and then just after the end of totality. And if you take a nice long exposure without clouds, you get to see the corona very clearly. And if you look carefully, you can see these streamers of gas. That gas is streaming along the magnetic field lines. If you did an experiment maybe in high school with a bar magnet and iron filings, you remember the iron filings line up along loops, and you're seeing here with the sun the gas lining up like the iron filings because the magnetic field lines stream out from the sun. And then the diamond ring effect occurs, and eventually, of course, the eclipse begins to end. So that was a good eclipse. There was another one last year that crossed over the Atlantic and right through Central Africa. Here's how it works. There's Africa, there's the moon, and there's the sun. So the sun was blocked by the moon from reaching West Africa. And of course, people flew there, drove there, did whatever they could. Here's a picture from West Africa. Here's a picture from Uganda, taken from an airplane during totality. Spectacular. A picture taken in X-rays. Of course, the X-rays are blocked by the moon, just as the visible light is blocked by the moon. So all this magnetic activity is being blocked by the moon. So the sun is extraordinarily beautiful and dynamic and active. We owe our lives to the sun. It's amazing. And there are these sunspots that are, well, quirky, if not bizarre. Yeah, there's this granulation, the miso soup, as I like to call it, the convection coming up from below, the hot gas rising. But in addition, there are these sunspots, very clear. There's a dark central region and a lighter outer region. To remind you, and to say it a different way, the reason spots look dark is that they are only 4,000 degrees Kelvin. That's excruciatingly hot, but it's cooler than the rest of the surface of the sun, which is 5,800 degrees Kelvin. So spots are blindingly bright themselves, but they still look dark. They actually look almost black in a photograph that was exposed to see the photosphere. The spot is glowing white hot at 4,000 degrees, but not as bright as the rest of the sun. So the spot only looks dark relative to the rest. How big are sunspots? Well, they're as big as the entire planet Earth. Here's a spot. There's the Earth for comparison in size. And you can see that spots are as big as the Earth, and the biggest of the spots are much bigger than the Earth. Think about how big the Earth is. You fly in an airplane to Paris, or to London. It's a long way. That's just a fraction of the circumference of the Earth. Earth is a big place. These spots, the little dots on the surface of the sun, are as big as the entire Earth. Now, just outside the photosphere is this thin layer of gas that's even hotter. I mentioned it when I talked about the hydrogen emission. You can see the layer of gas just outside the photosphere by waiting for an eclipse. During an eclipse, the moon blocks the photosphere, allowing you to see this thin layer of even hotter gas just outside the photosphere. And that gas is about 10,000 degrees, not 5,800, 10,000 degrees. And it's so hot that it glows like hot gas does. You see it glowing. Why is it red? Hydrogen. Hydrogen gas, the atoms excited to the third energy level, dropping down to the second energy level, spit off a photon that's red. Hydrogen alpha, it's called. You see the gas that's red. And if you look carefully, you'll see some gas that has flown off the surface, like over here and over here and over here. Gas is constantly exploding off the surface of the sun into that hot chromospheric region. So I want to tell you about those explosions in a second. First, to summarize, the chromosphere is hotter than the photosphere. It's 10,000 degrees. It's very thin, it's very patchy, but it's always there at some level. It emits a lot of ultraviolet light because it's so hot. Hot gas emits higher energy photons. So when you take a picture of the sun in ultraviolet light, you're seeing the chromosphere, this thin, hot layer of gas above the photosphere. So when you take a picture in ultraviolet light, you get to see the thin layer of gas that's so hot. If you're careful and you choose another technique using not hydrogen gas, but helium gas, you can get an even better picture of the sun. And in fact, I think this picture was taken in the light of helium, which emits all of its light in the ultraviolet. And with a filter like that, you can see these explosions off the surface of the sun where the gas is exploding off the surface, trapped by the magnetic field. And I have some video that shows some of those explosions. Here's a picture showing the explosions. The gas jumps off the surface, powered by the magnetic field, and is trapped along magnetic field lines, making bridges. The bridges are actually composed of the invisible magnetic field, but the gas hangs out with that. Yeah, it's funny. The gas hangs out, is trapped by the magnetic field. The ions and the electrons are trapped by the magnetic field. It's really spectacular to see that happening all the time. Beautiful arcs of gas because they're trapped by the magnetic field. And you can see it very clearly in images taken over the course of minutes and hours. Let's see if I can start this video. There we go. You see the sun looks pretty quiet. You can see the chromosphere. There's a magnetic field, and then wham! The magnetic field converts its magnetic energy into explosive energy, throwing the gas off the surface. I'll show you that again. The sun is often quiet. There's the granulation, the convection, and, I need to start this. And you can see a slightly magnetic region here, and there's obviously some magnetic activity along the surface. And then let me start the movie so you can see what often happens. The sun, apparently for no reason at all, converts magnetic energy to thermal energy, and wow, there's just these amazing blasts, explosive blasts of energy. Sometimes the explosions are so powerful that we call them flares. Watch this. Wham! Just amazing thrusting of gas off the surface as the magnetic field converts its energy into thermal energy. Here's that movie again. Kablam. When that happens, protons, electrons, hydrogen atoms, helium atoms get thrown off the surface of the sun and they escape. And they go streaming through the solar system, some of them hitting the Earth. And so we get blasted at the Earth occasionally by this so-called solar wind. The solar wind consists of particles, protons, electrons, and so on, that are exploded off the surface of the sun. And some of those explosions actually occur in the corona that I've already talked about, this 1,000,000-degree gas outside the surface of the sun. Quite beautiful because the magnetic field is entraining the gas. The corona is extremely hot, 1 to 2 million degrees. It's twice the size of the sun. It's very thick, but very tenuous, low density. The gas is so hot that the atoms are ionized. The electrons have been stripped off of the atoms. And so the gas being so hot, logically it emits mostly X-rays. And you get to see the corona especially during eclipses. Here's a nice picture of X-rays taken with a Japanese telescope, Yoko. So the sun is extremely active, and the corona is an amazing place with 1,000,000-degree gas and magnetic explosions. And I want to show you now a movie of a magnetic explosion that occurs in this corona. Here you go. There's the corona, and every once in a while there are these amazing expulsions of gas, explosions, where magnetic energy is being converted into explosive energy. This is just a real-time movie here. Minutes are going by. It's sped up. So every day of your life, you're living your life peacefully, minute after minute, hour after hour, day after day. The sun is doing this all the time with these magnetic explosions off the surface of the sun, throwing particles throughout the solar system, including hitting the Earth. These are called coronal mass ejections, and when the particles are flung off the sun, it causes a wind, a so-called solar wind that we've just been talking about. And that solar wind consists of these particles, electrons and protons, flying through the solar system. They extend all the way out to the edge of the solar system, and they pass beyond Pluto. So they actually go out into interstellar space. So this X-ray picture of the sun shows these explosions in the corona. Of course, a visible image also shows the solar wind in reflected light or scattered light. And occasionally, and this is just a quirk, a comet will fall into the sun, and while solar physicists are monitoring the sun, they sadly get to see the demise of a comet as it falls into the sun. The solar wind is kind of cool. When we're living our lives out here on the Earth, we are being bombarded by these electrons and protons coming in from the solar flares and the coronal mass ejections. We on the Earth are constantly being bombarded by these solar wind particles. The lucky thing, they're charged. Electrons with a negative charge, the protons positively charged. And when these charged particles hit the Earth's magnetic field, there's the bar magnet of the Earth. When they hit the Earth's magnetic field, those charged particles spiral around the magnetic field. They feel a magnetic force, and the charged particles spiral, and they get funneled into the North Pole and the South Pole. And if any of you have ever lived up north, say north of latitude 45 or so, you may indeed have commonly seen aurora, where the charged particles funneled in by the magnetic field hit the Earth's atmosphere. And when the charged particles hit the Earth's atmosphere, the molecules in the Earth's atmosphere are excited, and when they de-excite, they glow. And so you can actually see the solar wind when these particles that came from the sun, when they hit the atmosphere of the Earth, trapped by the magnetic field, spiraling in, lighting up as aurora, the so-called northern lights or southern lights. This is what it looks like. Some of you may have seen the northern lights, or maybe if you lived in the south, the southern lights. And of course, when a solar flare goes off, it takes a day or two for the solar wind particles to travel all the way from the sun to the Earth, hit the Earth's atmosphere, get trapped by the magnetic field, funnel down, and cause aurora. So you can predict a day or two in advance. When a solar flare goes off, the aurora are going to be beautiful. And that's in fact what happens. Also, these charged particles from the sun cause havoc with the Earth's ionosphere, and that screws up the radio transmissions, commercial, military, etc., on the Earth. And so a strong solar flare often causes radio transmissions to go out. It often can knock out power grids as well. The electrical power grids can be knocked out when a solar flare goes off, sending charged particles to the Earth. And of course, if you're an astronaut flying in a spacecraft in the space station or on your way to the moon, if you're an astronaut and a flare goes off, you're in big trouble. Those charged particles will pierce the vehicle that you're in, go right through the metal and right into your body and cause mutations and cancer. And so the astronauts that did go to the moon back in the late 60s and early 70s, it turns out were extremely lucky. It just so happens, while the astronauts were traveling to the moon and back, no large solar flares went off. No large coronal mass ejections went off. Otherwise, the astronauts would have been cooked, literally and figuratively, metaphorically. So, solar flares are a problem. And by the way, just as an aside, for those of you who are thinking that you might get to see the day when humans travel to Mars, maybe setting up a colony on Mars, the planet Mars, one of the giant challenges toward human spaceflight, Star Trek and Star Wars, one of the great challenges is astronauts enduring the high-energy particles that would come from the sun and cause serious damage to the, indeed, health risks that include death on the journey. So somehow spacecraft have to be designed in a way that doesn't allow the astronauts to be harmed. Now, let's talk about sunspots again. They are clearly due to magnetic fields because I showed you that the magnetic fields coincide spatially with the sunspots. The photosphere is often covered by sunspots, but they come and go. And as they come and go, people have tracked them for hundreds of years, indeed going back to the time of the Chinese dynasties over 1,000 years ago. People used dark glass, viewed the sun, and marked down how many sunspots there were on the sun and where the sunspots were on the sun. People were fascinated, going back to ancient times, by seeing with their own eyes, the Greeks, of course, also, seeing with their own eyes the spots appearing and disappearing and coming and going day to day, month to month, year to year. And so people started keeping track. And they found out a long time ago that the sunspots come and go in a cycle that lasts 11 years. The 11-year sunspot cycle. Every 11 years, there's a lot of sunspots. And then after a year or two, they die away. And a few years later, there are hardly any sunspots at all. And then if you wait 11 years, the sunspots reappear again. And in fact, it turns out that the magnetic fields associated with those sunspots change their polarity from north magnetic polarity, to south magnetic polarity. And so every 11 years, the spots come and go, but the polarity is different, and you have to wait another 11 years for the polarity to become the same as it was before. And so actually the cycle is twice 11 years, or 22 years. So people have been counting spots for a long time and studying spots. As I already mentioned to you, there's a dark region of spots. That's called the umbra. That's the darkest region, obviously the coolest region. And then this filamentary outskirts, you can almost smell the magnetic field lines causing the gas to flow along the magnetic field lines. That outskirt region is called the penumbra. These are just names. They don't mean anything. But I always am amazed to think that the spots are bigger than the planet Earth. I've mentioned that they're caused by magnetic fields. Here's how it works. You have the surface of the sun. There's the convection zone below. And every once in a while, the magnetic field from below ribbons up, pierces the surface, loops around, and comes back down, north and south. And for reasons that are fairly subtle, the magnetic fields trap the gas, force the gas to flow along the magnetic field lines, and reduce the heating that would have warmed up the surface to 5,800 degrees Kelvin. And so where there's a spot, the heating is less, and so the spots are only 4,000 or 4,500 degrees Kelvin compared to 5,800 degrees Kelvin for the rest of the photosphere. So the magnetic fields in some subtle way reduce the heating of that photosphere, causes the convection to do a less efficient job of heating the photosphere. And how that works exactly is not well known. But it's clearly the magnetic field that reduces the heating efficiency, cooling the gas, and therefore making the thermal emission less. So it looks dark. Now, the most amazing aspect of the sunspots, and frankly this is embarrassing, is that they come and go every 11 years. This is a graph that shows the number of sunspots detected visually. People just look at the sun and they record on a piece of paper how many spots they saw. And every day, day after day, there are people who do this for a living. Sounds a little boring to me, but some people love it. They count sunspots. And every day they have another entry in their table, how many spots they saw on Monday, Tuesday, Wednesday, Thursday, every day of the week, of the year, and of the decades. And then they make a graph, how many spots they saw over the course of time. And if you look at this graph, you see that the number of spots go down, up, down, up, down, up, down, up. A clear periodicity of 11 years. Every 11 years, there's a lot of spots, and then a few years later, not too many, and then within a couple of years, rises back up. The duration of time between peaks is approximately 11 years. Now, there's a few things that are strange and unexplainable about this graph, and that's why I said it's embarrassing, because astronomers don't know why the sun has an 11-year cycle. Something that even the Chinese and the ancient Greeks could see with their own eyes about the sun, we humans to this day still don't understand. Why do the spots come and go? And obviously it's the magnetic field that's coming and going every 11 years. Why do the magnetic fields come and go every 11 years? That's question number one we don't have an answer to. Second question, obvious to all of you, why is it that some years there's a lot of spots at the maximum, but other years at the maximum there are not as many? Sometimes more, sometimes a little less. And it's a little strange, but true, that this sunspot maximum, we're in it right now. Here we are in 2014. And if you look carefully, this is one of the wimpiest solar maxes in history. We're living through, right now, this year and last year, one of the strangest, weakest peaks. Nobody thinks it's going to get any higher. It's just going to drop down. And by the way, remember, look here, the last peak was in 2001. If you add 11 to 2001, you get 2012. Well, that was 2 years ago. So 2 years ago, we should have hit the maximum. That's right around in here somewhere. And yeah, we hit a maximum barely. It came a little late. But we're going to go downhill. That's why today was so lucky. We saw that beautiful spot group on the sun. But actually, we're coming off the solar maximum. Next year, there will be fewer spots. And the year after, fewer still. So we're on the downward slope here, and that's why today was so lucky. And yet I want to emphasize, astronomers don't understand why it is that sometimes there are more spots at the maximum and other times fewer spots. Yes?
And the book said that there was some time period where there were no spots.
That's a good, the question is about a time period when there were no spots at all. There was a period in the late 1700s called the Maunder minimum. And during about 50 or 60 years, there were no spots at all. And people were just stunned. And they knew enough from the time of the Chinese and the Greeks and through the Renaissance period that, you could count spots and keep track of spots. Why did the spots go away for 50 or 60 years? Obviously, that means the magnetic field went away. And by the way, if the magnetic field goes away, what caused the sun to turn back on magnetically? There's no light switch. There's no magnetic switch on the sun. So the sun has some dynamic, quirky behavior that we humans don't yet understand. And by the way, let me reemphasize, sometimes the maximum comes early and sometimes it comes a little bit late. So it's not a perfect 11-year cycle. Nonetheless, we are sitting here at the end of this cycle. And so it's I'm kind of sad because I know for the next, 7 or 8 years, we're just going to have fewer and fewer sunspots. I mentioned that people have been doing this for a long time. Here's the proof. Here's the 11-year sunspot cycle going back 150 years. Actually, just from 1850 to 1950. And you can see the sunspot cycle has been going almost like clockwork, but not a very perfect clock, for an awfully long time. And again, here we are at the end of this particular cycle. So it's sort of anybody's guess. What do you think the next solar maximum will be like? Do you think the next solar maximum... Well, first of all, when will it occur? Well, let's do the math. This is 2014. The maximum was maybe last year, 2013. Add 11. In 2024 will be the next sunspot maximum. So put that on your iPhone alarm clock. Let the alarm go off in 2024 to remind yourself that there will be a solar maximum somewhere over here. We predict, but who knows? And then here's another graph showing the details up to 2014. So it's rather interesting to wonder what in the world is going to happen next year, the year after, since we have such a puny, crummy solar maximum compared to the past years. And there's one last thing I want to say in today's lecture, and that is the spots not only have this rather stochastic, random character, but there's another aspect that's unexplainable, and that is that the spots, when they first appear, like in 2001, they appear at rather high latitudes. They tend to appear near latitude 20 or so, or minus 20. They appear in both locations. And as the years go by, the spots tend to appear closer and closer to the equator of the sun. And when the cycle is over, like it was in 2008, when the next solar maximum occurs in the sunspot cycle, the spots reappear back up at plus 25 and minus 25 latitude. In other words, well above the equator and well below the equator. Nobody really understands why it is that the spots change their location in latitude on the sun. So that's a particularly telltale aspect. And here's one graph that encompasses all of this. From 1900 to 2000, the spots come and go and come and go and come and go, come and go. And you see the latitudes where those spots were, and they change in a systematic way. This plot that shows the latitudes and the changing latitudes of the locations of the sunspots is called the sunspot butterfly diagram. And you can see maybe why they call this the butterfly, the sunspot butterfly diagram. And then one last note. Many of you were lucky enough to see that sunspot on the sun today. You saw it with your own eye. And what's interesting is that the sun rotates. It takes about 30 days for the sun to spin on its axis once. 1 month. Every 30 days, the sun goes around, spins around once. How do we know? You just simply watch the sunspots. If you watch sunspots day after day after day, you'll see the spots slowly rotate across the surface of the sun. The center of the sun rotates a little faster than the outskirts of the sun. I'm going to just say one more thing in today's lecture, and that is about the death of the sun. It's a little sad, but we have to face it. Someday, the sun, in its glorious burning of hydrogen into helium to produce the energy that we all depend on, someday, the sun is going to run out of all of its hydrogen, converting it into helium, and when that happens, the sun will not be able to burn hydrogen anymore. And so in that case, you end up with a star. The sun will be this way in 5 billion years. You end up with a star that has ceased to burn hydrogen and has converted it into helium. The center of the sun is slowly but surely being converted into helium, which it cannot burn. There is, of course, hydrogen just outside the core, like here. And it turns out that when the sun finally exhausts all of its fuel, all of its hydrogen, the sun will contract near the center, heat up, and that will allow the hydrogen gas just outside the core to ignite. And you'll get a shell of hydrogen around the core that can burn. Now that can only go on so long, a few millions of years. The sun will continue to die. And what will eventually happen is you just have a huge core of helium in the center. If you could freeze yourself and come back 5 billion years from now, you would see the sun very different from now. It would have exhausted all of its hydrogen, converting it to helium. And it turns out the sun will collapse in the center, heat up so hot to 100 million degrees, so that the helium atoms can burn in nuclear reactions. The helium, that's the ashes of hydrogen burning, the helium will become the new fuel. And here's how it works. 3 helium nuclei fuse together to produce carbon. In the center of the sun, 5 billion years from now, helium will fuse, burn, and create carbon. Energy will be given off in prodigious amounts, powering the barely revived sun. Our own sun will have this happen to it. It will be called a giant star because this energy production will puff out the sun, making it much bigger, and it'll be called a giant star. And these giant stars are the places in the universe where carbon comes from. You all know that life on Earth is carbon-based life. The organic molecules of which our bodies are composed, and all other species are composed, all other life forms are composed. The carbon ultimately came from nuclear reactions in the centers of giant stars. And so we owe the carbon that that makes up our bodies, we owe the carbon to nuclear reactions happening in stars. Here's what it looks like. 3 helium nuclei come together, forming carbon. like that. And if you could come back 5 billion years from now, the sun will be producing carbon in its center, glowing with a higher luminosity than ever. And the sun with that higher luminosity will fluff off layers of gas, puffs of gas, year after year, creating a nebula of gas around the sun. And we see this in other stars. They're called planetary nebulae, and I want to show you a few pictures of these planetary nebulae as the giant stars fluff off their gas. They look like this. Our sun will look like this in 5 billion years. The dying sun in the center and the gas fluffed off by that giant star around it. Other planetary nebulae look quite different. Here's another one. The Twin Jet Nebula. The first one, of course, is the Cat's Eye Nebula. Here's some more of what our sun will look like in 5 billion years. The Ring Nebula. And here's one of my favorites, the Hourglass Nebula. Beautiful puffs of gas, ionized and heated by the dying sun-like star in the center. And of course, in the center is where all that carbon is locked up in a dying dead star because the star can no longer produce enough energy to warm itself up, so it dies like an ember on the campfire. So I'm going to stop there, and next week, after we're done with the sun this week, we're going to go back and talk about Jupiter and Saturn, the moons of Jupiter, and the rings of Saturn.